Hi, in this second part of getting started with FPGAs, I'm going to build a simple lab timer with a hundredth of a second precision. It will operate on the Albert S7 development board and display on the multiplex 7-segment display, so that only gives me 4 digits to play with, but it'll be enough. I wanted to try a project based on clocking, timing, latching values, because these are absolutely fundamental parts of pretty much every digital circuit. So here's a simplified diagram that shows the basic design. So it uses a 4-stage binary coded decimal counter, and I've shown it with carries between the stages, and it's connected to a multiplexed display. So we need a 100 Hz clock for the counter and a bit faster for the display. In theory, this isn't really a very demanding design at all. We just divide the 100 MHz board clock down to get the 2 different rates that we need. And while that will work in this application, it only actually works well because the application is so slow. In practice, there will be glitches in the counter carries and things like that, and they may be invisible at this speed, but it would matter in faster designs. Also, while the clocks in this application don't actually need to be tightly synchronized at all, that's not usually the case. Anyway, I'm going to show the build in stages, but I'll be focusing mainly on the new things, and I'm not going to repeat the workflows that I showed in part 1. If you need those, then I'll include a link. First up though, I'm going to deal with the 7-segment encoder, since that's just a simple piece of combinatorial logic. It's almost a lookup table. And then I'll look at the multiplexer and the quick and dirty clock source so we can actually see something. And then I'll sort out a counter and refine the clock handling and add some synchronization so that we've got some good practice in there. Anyway, here's the outline of the segment encoder, and I'm going to show the basic Verilog in Notepad++ so that I can make the text big. So let's have a look at the code in a bit more detail. So here's our 7-segment encoder module name, and then it's followed by this new block, which is parameter block. So they're like design time configuration. So I've got 2 parameters. One to say I want to use binary coded decimal as opposed to full hexadecimal. If I set it to 0, then I want to display the characters 0 through F. If I set it to 1, then I want to display only the characters 0 through 9, and I'll display a blank for everything else. The other one here is common anode. I want to write all my logic in a positive sense. So 1s mean on and 0s mean off. So on the 7-segment display, anything with a 1 is lit up, anything with a 0 is not lit up. So that's the idea. But of course, in the real world, I might have to deal with common anode displays. And in fact, the display I'm using is common anode. And that's probably the most frequently used. So I've set the parameter value to 1 for that. Now, these are the defaults of these parameters. When I use the 7-segment encoder, I'll have to create an instance of it in another piece of Verilog somewhere. Then override these parameters and give them new values if I want. Now, if we look at the code that's using the common anode parameter, here, if the common anode has the value 1, so it's true, then it assigns an inverted value to the output. That's what this little tilde symbol does. But if it's got a false value, it assigns the non-inverted value instead. Now, if I pass common anode through the port, it implies it can be changed, so both signal paths have to be built, and then there's a multiplexer probably just to choose between them. But a parameter is constant, so it only needs to build the one that was specified when we create our instance of the module. So this is a fundamental step in creating flexible, reusable modules. Okay, here's our port. So we've got our binary value coming in. It's 4 bits wide. We've seen this before, it's a wire. Further down, you can see that we've got an internal variable, and it's called temp segment out. It's going to hold the pattern that we're going to output to our display, and then we're either going to invert it or not invert it and pass it to the actual segment out. In the previous video, we saw wires and we saw reg. The difference is, of course, that a wire joins pre-existing things together, and that reg is an assignable value, so it's a variable. Now, logic is also a variable, but it's a bit more flexible because we can either use it as though it's a wire or we can use it as though it's an assignable. What we're doing really is just removing the emphasis from our brains, having to keep track of everything, and just letting the computer do a bit of the work for us. So SystemVerilog has a few more variable types compared to normal Verilog. And I should just highlight here that SystemVerilog and Verilog are the same thing. SystemVerilog is just the next iteration. For some bizarre reason, the powers that be decided to give it a new name. It wouldn't be confusing if they hadn't given it a new name. Further down, here's a new SystemVerilog always statement. So previously we saw always at star, which I used for a combinatorial procedural block describing some combinatorial logic, but using procedural behavioral description. But there are limitations to that block because it's in fact actually quite a general purpose structure. So SystemVerilog actually makes much more explicit use of always combinatorial, always latch for latching blocks, and always flip-flop or always FF for clock-driven blocks. So the developer's intentions can be made explicit, and therefore you get much better semantic and syntax checking. Now, I'm not going to delve into it too much, but you can explore and research the lists above at your leisure. Okay, so let's have a look. We've got an if statement here. So this is for blanking. And as I said before, this is for common cathode. So we're assuming a positive logic where 1s is a lit segment and 0s a non-lit segment. So yeah, turn it off. Then we get this case. So if you're used to C, Java and things like that, then you'll be used to things like a select or switch statement or something like that, depending on your programming language. This kind of just wraps it up a bit more succinctly. Case, bin in. Well, if it's 0, then I want this pattern. If it's 1, I want this pattern. If it's 2, I want this pattern, and so on. We're just choosing which pattern we fancy using. And so this is pretty much the equivalent of a directly programmed lookup table. So what else have we got? Well, we've got this little bit down here where we've got BCD question mark. So this is saying, if BCD is true, so here we've got our little binary coded decimal flag. So if binary coded decimal is true, then set this to 0. If it's not true, then we'll use that value instead. And remember, this is coming in as a parameter, so it actually just builds one version or the other. We've got a default down here, and this says just to guarantee no latches. Okay, so we come down here, we get to the end of our combinatorial block, and just here we can see that I'm assigning segment out to be either the inverted version of the temporary segment or the non-inverted version, depending upon that parameter again. So that's it. Pretty short, pretty straightforward. Only took a bit of talking about because there's a few new things in there. Since this code is going into a library for reuse, I'm going to want some proper documentation, at the very least some good comments at the top of the file. My minimum standard is you should be able to use it to write the unit tests. Now, in an ideal world, you have someone to write a spec to a high standard, then different people use it to write tests and code. These come together and the outcome is recorded, and as a result, the specification is clarified as needed and goes back with bug reports to the developer and tester, and it goes around the loop until all is well. Now, I don't have a test team, but writing test code should be quite mechanistic, so I decided to give ChatGPT the job. So I wrote out my specification in a way that I could put into my comments at the top of the file, and then gave them to ChatGPT along with a little statement telling it to write a test script for me in SystemVerilog, and that it should report passing and failures of each test. I did have to go back and do it again and just add in that it's using Vivado 2025.2. And the reason for that is it produced perfect SystemVerilog, but like all other manufacturers, Xilinx or AMD, they don't necessarily support all of the SystemVerilog standard. So anyway, it produced ultimately a lump of code that I could use. So here's the first run of the test bench, and one of the things you can see quite interestingly is that it tells me that I've got an error in the test for blanking plus DP. So the decimal point is supposed to still be shown. So if we've asserted the decimal point is showing and we've blanked the digit, is still supposed to show the decimal point. If you're doing leading zero blanking, you might want to blank the 0 but still show the leading decimal point. So decimal point can be blanked anyway because we just don't send it. So we don't need blanking for the decimal point. So yeah, it was expecting the decimal point to be turned on and it isn't. So yeah, so why is the big question. Well, let's have a look at my 7-segment encoder. Let's have a look at the blanking then. So just here, we say if blank in temp segment out equals 8 bits, including the 0. There's the else, not blank. And there we go. We're setting the temporary segment within the not blank section. It needs to be outside of the not blank section. And also, instead of setting all 8 bits up here at the top, we need to only set 7 of them. So, okay, so that makes sense. It's done its job. It's found a mistake that I made. So there we go. We'll move that temp segment to outside of the not blank, so it will behave all the time. And then we'll change this to 7. So we're not setting the top bit either way. And fingers crossed, if I save that, and then we'll close the simulation and rerun it. By the way, on the left-hand side here, you can see that I've got multiple simulation sets. And this time we went all the way through to the finish, so I'm hopeful. And there we go. And there's our test passes all the way through. So that's absolutely perfect now, but it just illustrates how simple it is, even in a simple piece of code like this, to just make a tiny little slip up in the placement of a statement. And although you think it's working, it's actually got a subtle error. So very good news, that test bench worked really nicely. Okay, so I want to deal with the multiplexing of 4 digits onto a display, but for that I need a clock source. So the idea is that we have a 16-bit binary coded decimal number, and we iterate through it 4 bits at a time, take those 4 bits, encode them, and send them to one of the digits on the display. That's on briefly, and then it's turned off, and the next one's turned on and has its 4 bits encoded and briefly displayed, and so on. And persistence of vision makes them look like they're all lit together. Now, you may remember that I need 2 clocks for this, one for the multiplexer and one for the timer counter itself. So I decided to make 5 kilohertz for the multiplexer. Now, normally I'd use about 80 to 100 hertz per digit, so I'd only normally aim at 400 hertz for this. That's fast enough to perceive without flicker. But for YouTube, I'm using a faster clock so that it interferes less with the video camera shutter, otherwise it will appear to flicker. Now, one way to get a pair of clocks with minimal logic like this, and it would work, but it's horrible, is to put the dividers in series. So we first of all divide it to get 5 kilohertz, and then we divide that down to get the 100 hertz. That will give you clocks of the right speed, but every divider adds propagation delays and distribution delays, and everything goes out of phase in a very sort of undetermined way. Now, we can do better than this. The simplest sort of solution is to use 2 identical dividers, but they use the same clock source. So in actual fact, they end up in sync with each other within a few picoseconds because they're using the same edges from the same fast clock. It's often good enough. Now, it doesn't pay any attention to improving jitter, there's no temperature compensation, potentially the routing of the signal isn't optimal, but I'm going to talk more about that later when I do the actual critical 100 hertz part. For the moment, this will absolutely suffice to drive a display. So here's our simple clock divider module, and let's start off with the parameter here, toggle clock cycles. So we've got an input clock, which is say 100 megahertz, and we need to divide it down. So we can time our output clock by how many of those cycles it needs to divide by. So if, for example, we're going from 100 megahertz to 1 megahertz, we need to divide by 100. Now, we actually need to toggle our signal, our output signal, every 50 because, we've got a high period and a low period per cycle. So rather than risk someone feeding in something like 99, a number that won't divide by 2, then actually it's easier to actually just say how many clock cycles do we stay high, followed by low. And this way, actually, we could replace this with high clock cycles and low clock cycles so that we don't have a 50% duty cycle if we wanted to. Here's our input port. We've got an input clock and we've got an output clock, as you would expect. Now, I've done nothing in here in terms of making sure this is distributing on the clock distribution network in the FPGA or anything like that. Then just treating it as though it's a logic signal for the minute. We can pick all that other stuff up later on. I should point out that I'm initializing it to 0 in the actual port definition. And then we're down to here. So I need something to actually do the counting. If I need to count 100 clock cycles, I've actually got to count them. So I need a counter variable for that. So here it is, logic counter. And I need to define how many bits it's got. And that's where this $CLOG2 comes in. So this means the ceiling or the rounding up of the logarithm to base 2 of whatever's in the brackets. So if that was 128, log 2 of 128 is 7. So we need 7 bits to store the number 128, and that's correct. We do, exactly. The thing is, though, of course, we actually start our array at 0. So we just need to subtract 1 from that. So this $CLOG2 literally just gives you how many bits do you need in order to store that many numbers. And again, we initialize it to 0. Now, we've got 2 options then, really. I'm going to come back to ORSFF in a second. We can look at our counter and we say, have I reached that number of counts? Well, to begin with, no, I haven't. So I'll do the else statement, and all I'm going to do is increment the counter. Right, so if we have reached the limit then, so we've done our counter plus plus, and we do that every clock in. We just increment our counter. But eventually I do reach the number of clock cycles that we're interested in. And so what do? Well, we assign the counter back to 0. And we assign the clock out to be the inverse of the clock out, exactly as you saw with the simulation in the previous video. Now, I suppose I should mention the fact that this is an assignment, and so is that. So counter equals 0 or counter equals 0. So why do we use this one? Well, this is what's called a non-blocking assignment. And what it guarantees essentially, let's look at clock out. So clock out is the inverse of clock out. What we mean by that is, as we enter this, clock out has a value already. So we're going to invert that value that it is already, and that's what's going to be stored in our flip-flop for next time round. But what happens if I do this? I know this is a silly example, but hopefully it will make the point. Well, the answer is it works fine. It will just throw that one away because it's a waste of space. But it will work absolutely fine because this clock out on the right hand side is always, because this is non-blocking, that's always the value as it was when we started this. If, however, I change that to this type of equals, then it actually builds a sequence. It says clock out must be made to equal the inverse of the clock out when it arrived. and then in this one, and then I want to take that result that I've just calculated and I want to invert it again. So that actually will do nothing. It will invert it and then it'll invert it again and it'll be back where it. Obviously, that's not terribly helpful. Even if you've got a legitimate reason for doing that type of thing, it's a bad idea because don't forget clock out is actually meant to be a flip-flop. And we know that because we're in a block called always flip-flop. It's convenient to think of clock in arrives, the positive edge clock in arrives, and then all this happens. But that isn't really the case. Everything in here that's derived, so clock out or counter, these are all assigned values inside this block. They are to be stored in flip-flops. Doesn't matter what type of flip-flop, it's to be stored in some form of flip-flop and remembered. And when do we store it? We store it when the clock in arrives. We do not start calculating it when clock in arrives. We've already worked it out. We just clock it in to the flip-flop at that point. If you imagine we're starting at time 0, we've already got a value for clock out and we've already got a value for the counter. This already exists, so it's already doing the calculation. This is on the left-hand side of the circuit, already doing this calculation. And when this clock in arrives, it just clocks the results into that flip-flop. So the time between that positive edge arriving and there being new values in the flip-flop is just the propagation delay of the flip-flop. None of this other stuff counts. As long as this can be done in one clock cycle, then you will get your clocking in happening in a few hundred picoseconds. Okay, back to the multiplexed display then. This slide shows the outline design. So we start life with our clock, that feeds into a counter, and it counts down 3, 2, 1, 0. Then back to 3, and so on. It's counting down because digit 3 on the display is on the left-hand side, and that's just actually to keep all the bit ordering consistent throughout. And later it will be easier to do leading 0 suppression working from left to right. Now that 2-bit counter is decoded into 4 wires that feed the common anode or common cathode transistors in the display. So just one wire at a time is actually connected. Now the 2-bit counter also acts as a selector in a 4-bit wide 4-in-1 multiplexer. And as we'll see later, that's actually just a very simple single expression. And the 4 chosen bits are encoded and sent to the individual segments of the display. So here's our module. To begin with, of course, I've got some parameters going in because this is the type of thing you do want to drop into your development library. You don't want to write this multiple times. It's not stretching, but you don't want to do it again and again. So anyway, 4 digits long, please. I'd like it to be common anode. So I've actually made the parameter common cathode this time so that it matches positive logic. I talked about that earlier, wanting to make everything in a positive sense. I'm going to rename the one in the other file later. So currently in the encoder, it's called common anode, which means that down here where I use it, I have to invert it. So I'm going to rename that in the other file as well. Whether or not we're going to suppress leading zeros, and whether it's binary coded decimal or hexadecimal. And that one literally, I mean, you can kind of see from the highlighting further down that all we do is we pass it through to the encoder. We've got some inputs. We've got a clock input, of course. And then we've got this wire here, which is the binary input. So this is 4 bits wide. We've seen that before. But now we've got another set of expressions on the right-hand side here. So this is an array. Since digits -1 is going to be 3, this is an array of 4 4-bit inputs. So this is called a packed array on the left-hand side here because this 4 bits here are meant to, they're 4 bits of a single thing. They're 4 bits that can be treated as a unit. So we can assign the number 0 through 15. These, however, are what's called an unpacked array. So this is saying there are 4 lots of it. That's not the same as a 16-bit input. There are 4 4-bit inputs. Okay, so what else we got then? We've got this decimal point mask. What I've got there is a bit for each of the digits, so we can turn on the decimal point in any digit that we like, any combination of digits we like. The reason I've got that instead of a position is that for colons in a clock, you might need multiple of them turned on simultaneously. Doesn't make much sense for decimal points, but for colons it definitely does. And then we've got outputs for segments and the relevant number of wires going out to trigger the transistors for the common cathode or common anode. Next up, we've got this little bit of variable here called isBlanking, and this will be used later on for leading 0 suppression. It was helpful just to have the variable in existence now. I haven't put the leading 0 suppression in just yet because it will kind of make a bit of a messier set of code. It's quite nice and simple as it stands. Here's our counter. So first of all, we have a variable to hold the counting, and we just make it big enough. This is the CLOG2 that you saw before, and that's just assigning a variable width which is big enough to hold the count that we're interested in, which in our case is 3 through 0. Here's our actual counting happening. So always FF, we've seen that before as well. It's a flip-flop triggered by clock in. So every time clock in happens, then we will update the value of counter. This here is an if-then statement just compressed into one line. Again, we've seen it. So if the counter has decreased all the way down to 0, because we're counting down from 3, 2, 1, 0. So if we've reached 0, it's actually time to go back up, and in this case to 3. So this is there's a question mark. Here's our true statement, and here's our false statement over here. So if we're not at 0, then we can just subtract 1 from the counter. Let's move down. Here's our 7-segment encoder. So you can see that this is just an instance that's called encoder. We've set it to binary coded decimal. Currently, because it's got an input called a parameter called common anode, that is the opposite of common cathode. But when I rename it, then obviously it will just be a straight pass through. This is our multiplexer right here. On the diagram, we had a multiplexer just here. And there it is. It's that one line just there. All we're doing is selecting the right one from this array of inputs. And just that's what gets passed to our encoder. Here's our decimal point mask. So again, we're using exactly the same technique. We just pick, in this case, so in this one, counter is choosing the right entry in the array, because in order to drill down into this, first you have to pick which one of the 4 array entries you're actually going to use. And then you can drill down into these bits if you want to. But the first statement is always, which of the array entries is it? This hasn't got an array entry, so we go straight to the individual bits. So there we go. So that's just picking the right bit, single bit. This is whether or not it's blanking. So if we're 0 blanking, then we might blank it out. And this is connecting the segment outputs, the 7-segment outputs, to the 7 segments in the next stage up. Pretty much passing them out to the hardware. This section just here, which is the binary decoder. So we want to take our 2 input bits from the counter and turn them into 1 of 4 outputs. And again, it's surprisingly simple. So what we do, first of all, is we say, okay, we'll set all of our digits to either a 0 or 1, depending whether it's common cathode or common anode. And that's what that leading tick means just here. So you've probably seen lots of numbers like in this slide, where the left-hand side has the width in bits, then an apostrophe or tick, and then the radix, such as binary. But the rule is that if we don't put enough bits in the right-hand side of this, it will pad all of the spaces with zeros. Where we might want to use different sizes, this can be a problem if we want to replicate the same value, like a 1, into all the bits. So in SystemVerilog, we can miss off the size, and it simply fills all the bits in whatever we happen to be filling with the value that you give. So in this case, a whole lot of 1s. If you don't put the tick in, then it will equal 1. So you'll have a load of zeros on the left-hand side of the variable, and then a 1 in the right-hand digit. That isn't what you want. You want it to be full of 1s, and that's a quick way of doing it. Okay, the next thing then, of course, is that we want to turn on only one of those digits, and that's very straightforward because it's whichever one the counter is pointing at, and set it's common cathode. So common cathode is 1 if it is common cathode, or 0 if it isn't. So we're essentially either filling this with 1s and then setting one of them to 0, or we're filling it with 0s and then setting one of them to 1. So again, as we saw before, we're using always comb instead of always at star, and that's how we get the extra error checking. If, for example, just here, instead of using this very inclusive and comprehensive statement, I'd use an if statement. I could easily have forgotten the else. And in Verilog, that would create a latch. And we definitely do not want a latch on this digit output because that would turn on multiple digits simultaneously, potentially. So it's useful to use this because it will do additional error checking and make sure we do everything sensibly. And that's it. So if I plug this into a really simple top-level module, like this one, then it should hopefully output a number into all 4 digits. So here's my lab timer. I've got an input clock in. This is the 100 megahertz off the board, and I've got it connected up in this constraints file. Pin D14 is my input clock, and it's 100 megahertz as it happens. And here are my segment outputs. They're connected to various pins, B14, A14, A15, etc. And here are my digit controls as well. So that's what's going into my constraints file. For the moment, I'm leaving the reset and the switches out, but that's pretty much it. So all I'm doing here then is just wiring things together. So here's our simple clock divider. It's set to give me a 5 kilohertz clock, and it outputs into display clock as just a wire. Here is the timer logic, which doesn't exist yet. So all I've done is I've set a literal timer count of 0, 1, 2, 3. So hopefully I'll be able to see those appearing in the right places on the development board when I run this up. And then I just connect all that up to the display multiplexer and let it go. And here it is. It has built. Happy days. Now, there will be quite a lot of messages, I think. Not as bad as I feared. So we haven't actually told it that the clocks are clocks. We've just kind of treated them as inputs that happen to clock up and down, and we've connected things together. So timing, there are no user-specified timing constraints. So timing is needed for proper timing analysis. So in actual fact, we don't have any synchronous outputs or anything like that in this, but we can see that we've got 14 outputs or something like that, and a few inputs, and it wants to verify that everything is lining up nicely, and it doesn't know how to do that because we haven't told it that it doesn't need to bother. So it's warning us about that. The next one down here is power usage, and it's saying there are no user-defined clocks because we haven't told it that the input clock is a clock, and we haven't told it that our 5 kilohertz derived clock is also a clock. It says power estimation will be inaccurate until this is corrected. Now, I've looked at this a few times, and I can tell you it will be wildly inaccurate. And yeah, of course, that's complete rubbish. And this is really basically saying, look, you've done some bad things up at the top here. So yeah, really? You really want to program this? Anyway, we're going to program it. So I'll try and keep fairly steady hands as I record this. And we'll get this programmed in. So 0, 1, 2, 3. What we shall hopefully see is the number 0, 1, 2, 3. It's not as clear as I'd like because the lighting isn't the best, but hopefully you can see that we've got the right digits and the decimal point in the right place. So all is well so far. Okay then, it's now time to deal with our 100 Hz clock and our timer, and that's all of this section just here. So this is the bones of the application. Our first attempt might be to actually just do what it shows on here. Here's our possible first attempt. So we take our 100 MHz clock, we divide it by 1,000,000 to get 100 Hz. Well, that seems to make quite a lot of sense because however we do this, we need a 100 Hz signal in order to count at 100 Hz. And then we pop it into a 4-stage counter. So we actually have 4 binary coded decimal counters that can count up to 10. And we use the carry from those to trigger the next counter along in the chain. And that will work. And I'm going to build it and show you it working just to demonstrate. But I would actually like about a 5 nanosecond precision on this. Although the resolution is 10 milliseconds. I want a very precise count, and I'm not going to get it. And there are various issues. So I've said at the top here that this confuses the control signals, clocking signals, and data signals. They're all mixed up together. You know, this binary coded counter should be a counter, but it's actually a clock divider as well. So here's our problem. We've got 4 generated clocks in here. So we've got a 100 Hz clock, and then this counter here outputs a 10 Hz clock, this one outputs a 1 Hz clock, and then a 0.1 Hz clock. This whole process, this chain here, is very sequential and it's very slow. And if we think about it, this first character here is outputting the correct value. This one is still not updated yet, so it's not correct. This one isn't correct. And as we get carries, we get huge glitches and invalid data being output from the counter. Now, at 100 Hz, those glitches might last, let's say, 5 or 6 nanoseconds, so we're never really going to notice them, and always they will settle down to the right value. But if we're doing something faster, it would be a disaster. The next problem is the reset. We can't do a synchronous reset because this one here, you'd have to hold the reset button down for 10 seconds to be sure that you've got a reset. That's hopeless. So we have to do asynchronous resets, and they're not ideal, but it would be nice not to have that kind of enforced like that. I'd like a choice. The next problem is the enable, and the problem there is our enable is asynchronous compared to this 100 Hz. There's no choice in the matter. It's a button or a sensor or another piece of equipment completely independent from the timer that's turning it on and off. So it's asynchronous. There's no two ways about it. If we look at that as a signal, so this top one is our 100 Hz clock. This bottom shape here is our enable signal, and I've said it's elapsed for 0.043 seconds. So in terms of elapsed time, it should count 0.04, but it doesn't. Depending where this is, depending where it's timed versus this clock pulse, it might count 0.04 or it might count 0.05. We don't know, but what we do know is we potentially have a +1 error in our last digit. So these are the problems that we can see with this. Nevertheless, it looks visually like it's working. But what I'm going to do in a minute is I'm going to come back and start dealing with some of these problems. First, though, let's take a look at the code for these slightly flaky attempts. So here we go. And first of all, we'll take a look at our top level module. So we can see the original display clock up here. We've got the original multiplexer down here. No changes there at all. All we've done here is we've added that 100 Hertz clock. And the way that we've done that is exactly the same as we did for the 5 kilohertz clock. We've just created another instance with a different parameter. That's all that's happened. So we don't need to look at that code again. Already seen it. What we've got then is we've got that feeding into this multi-binary coded decimal counter with carry. And we've called that timer. That defaults to 4 digits, so that's fine. Don't need to pass any parameters into that. A couple of other inputs. We've got an enable input for running. So enable is the board connection, the switch on the board. Reset is the switch on the board. And these are the two inputs that I've chosen to call them in the module. That's all. And there's our binary coded decimal out. And that timer connects through to the multiplexed display. And, that's it really. We just replaced our constant up here with a connection to a timer. So let's take a look then at the multi-binary coded decimal counter. Here it is. And I'm going to come back to this in a second, because what it does is it contains instances of binary coded decimal counter with a carry. That's this. And all this does is it counts from 0 to 9 repeatedly. We can see that it's got an input called clock input, which is fine. That's what it's going to clock with. We can see here that it's got an input called running in. So it is running or it isn't running. And we've got a reset as well. And then we've got an output, which is 4 bits, which is binary coded decimal output. And we've got a carry output as well. So let's take a quick look. Always flip-flop. We've seen that before. This time, though, we've got 2 things in the sensitivity list. We've got the clock input, and we've also got a reset. So this is because I want my reset to be asynchronous, because, as I said on the slide, this divides the frequency down, and therefore we would have to hold reset low for an awful long time to guarantee that if we just use clock as a sensitivity list, that we actually pick up the reset. So just here, this is where we do the reset, and we always do reset like this, and it's always first. And that's because we're going to assign BCD out to 0. So we're going to reset it to 0, of course. Now we can only assign, legally assign, only assign to that particular variable in one process block. So we can't have a separate process block that captures the reset in and sets binary coded decimal out to 0. It has to be in the same block. So it's very convenient just to always make it the first statement to handle the reset. And then if it's not being reset, then we do the rest. Now this way as well, should we hold the reset button down, it continues to hold it in reset. The next thing is the running. So this is the enablement section really. You would often see if enabled as the criteria here. So first we do reset, then we do enable, then we actually just do the logic. That's the order of things, always the order of things. This is just like we saw before with the previous counter. If BCD equals the terminal digit of 9, then we're going to roll over and we're going to make it 0. And we're also going to set the carry bit. If we're not at the terminal digit of 9, what we're going to do is we're just going to increment the output and we're going to set the carry to 0. And that's our lot. So the carry literally, every time we roll over from 9 to 0, the carry literally pulses high for 1 clock cycle. And that's it. Now the clock cycle on this, of course, is 100 Hertz, because that's what's coming into the first one of these. What I need, of course, then is a string of these in order to make my 4-digit counter. And that's what this does. You can kind of see we've got the clock, we've got the running, we've got the reset. Instead of one binary coded decimal output that's 4 bits wide, we've got a set of them, 4 of them in this case, because there's our array, just like we saw before. Now, I should actually make a note here for you that here I've specified BCD out as 3:0. Now you can also put a 4 in there and it will create 0:3. Now just keep in mind that if you're putting things in there and then reading them out again later, that you might be reversing the order if you don't always call them the same thing. Unfortunately, in most of my code in this so far, I've done them the other way around as though they're the bit width. I'm going to go back and change them all later. But yeah, if you swap and change between them, you're changing the order of your signals, unfortunately. So yeah, so I've done 3:0. Really, I could have just put the word digits in there and that would have been great. But consistent throughout. So what have we got going on in here? Well, we've got the carries. And what I've done here is I'm collecting a carry for each one of them. And I'm going to string a whole load of these together. So first of all, I need one which I'm calling BCD 0, and that's taking the actual clock input. Further down, I've got this Genvar and generate block. And what that's going to do is all it's going to do, so I've created a variable called I, which I'm using in a for next loop here, and it's going to create a number of copies of the module. I've created instance 0, if you like, that's going to deal with digit 0. So I need to deal with digits 1, 2, and 3. So there's my for loop that's going to generate I is 1, I is 2, I is 3. And then it's going to create an instance called BCD, and then this will be _1, _2, _3, depending what my value of I is. And it will then do this bit. So you can think of it as replacing all the I's with numbers and writing out this code multiple times for you. It's a generate block. It does what it says. It generates code for you according to the loops and things like that you put in. So the end result of this will be 4 of these BCD counter carries. So the first one will be connected to the clock and will output its carry into this little vector of carries, and it'll put it in position 0, and then the next one will use its carry as its clock. So it is its clock in is the carry of the previous digit. It puts its output into the right place and it stores its own carry into this vector of carries. And that's it, just chains them all together. It's just a simple way of doing that, and truthfully you really don't want to do this way at all, because what you're doing inherently is you're using the logic of all these carries, which are really just numeric bits of data. You're using those as actual clocks. So I wanted to show you this. What I've done is I've run up a simulation on that counter, the one that I don't like. In order to do that, by the way, yeah, I did have to actually just add a little bit of code, and it's just here. It's this bit here. So what this does is it takes the SystemVerilog structure here with its unpacked output, the array. And unfortunately, despite the fact that this has been in SystemVerilog for 20 years, and Vivado apparently supports SystemVerilog, evidently its simulator does not. So it simply throws away the port definition for that because it doesn't support it. The solution to that is that we provide 2 outputs, one which is SystemVerilog friendly, which is the unpacked array, and one which is Verilog friendly, which is repacking it back into an old-fashioned flat, in this case 15-bit wide, 16-bit wide vector. That is both Verilog and tool friendly. So we don't have any surprises if we want, and I think this is probably a good thing to do anyway, because you want it to work with both Verilog and SystemVerilog. There's the code to do that. It's one of those little generate blocks again, and all we're doing is we're going through, and this is an assignment, so all we're doing is we're creating wires, we're creating nets, and defining that certain outputs in this nice unpacked output are being connected through to certain bits in this packed output. That's all that is doing, just joining everything together with wires or nets. Anyway, the output looks like this. So the first interesting thing is that it's taking nearly 5 nanoseconds before we get any change in the output at all. So here's our change just starting. We're going from 3999 to 4000. The reason I've chosen that one is because it's got a carry quite a long way up. So we can kind of see it at its worst almost. But there's only 4 digits, don't forget. It's not exactly a big count. A large portion of that time delay is the amount of time it takes to route from the latches all the way through the output buffers and through the output pins. But what we're really interested in is how long we have invalid data coming through. I'm running this simulation at 100 megahertz, and that's so that it would actually finish today and not in 10 days' time, because I need a lot of transitions to get a lot of data so I can look at these clearly. So just here, this blue marker is where we start changing from 3999 onwards. So we're just starting to get our results latched into the output of our flip-flops just here. Now what I've done is I've got the scale set up at the bottom so that it's relative to that start point there. So that's marked as 0 picoseconds on the bottom. And then I drag my cursor across and you can kind of see that there's 3999 and then it changes some other value, then 399C, something else, 3900, 3800, 3000, something else, 0, and then finally it gets to 4000. How long is that? Just shy of 3 nanoseconds. So of the 10 nanosecond clock pulse, 3 nanoseconds is completely invalid data. So almost 5 nanoseconds is the previous value. Of course, this is on an output pin. And then we've got an invalid period of nearly 3 nanoseconds where the data is just all over the shop, and then it settles after about another 3 nanoseconds. So from the leading edge of the clock, over 7 nanoseconds. So well, that's pretty awful. So you can see very easily that if we either increase our clock speed significantly, so if we run this at 200 megahertz, then we wouldn't have our output before the next one was being calculated. So things will be changing and interfering with each other very, very quickly. And similarly, if we significantly increase the number of digits that we're counting, then this nasty period would expand further out. So yeah, so not a good design, really. Not something you want in your toolbox for future use, that is for sure, because although it will work in this application, you're going to fall over it in future. So yeah, poor solution. So on reflection, I've not yet covered everything I planned, but I think this video has enough content and enough new things to think about. And I've got a working timer, although it's perhaps not yet to my desired standard. So I'm going to call it a day and get this published, and then I'll add in a part B in a few days in which I'll look at some of the best practices and how I can refine these modules to a higher standard. I'd like to be clear that the best practices are not just for FPGAs, but digital circuits in general. Anyway, I hope you enjoyed progress so far. Please remember to like, subscribe, comment and share, and I'll see you for part B. Bye for now.